0.3 molar NH3 is titrated with a 0.15 molar HI solution. Let's just stop right there and draw a picture for ourselves. Pictures are usually worth 1,000 words, so let's do that. We have a beaker here, and in that beaker is just ammonia. Need you with me? Need you with me? All right, 0.05 liters. All right, that's what you're starting with. Everybody agree with that picture? Yeah. And all you have is base. That's all you have. Okay? He's floating around all by himself. Anything come to mind? Dissociation comes to mind, which means K is equal to X squared over molarity. So that's what's got to come to mind like that. It's got to start coming to mind like that. Now, when it says it's titrated with this part right here, then I'm going to draw a little burette, and we're going to do a lab where this will come to life a little bit better. There's my burette, and in my burette is a 0.15 molar HI. Half the molarity of HI that I have of NH3, agreed? Very important that you notice that. That means to get to the equivalence point, you need twice as much volume because the molarity is only half. If the molarity is only half, I'll need twice the volume I started with. If their molarities were the same, I would have to add in the same volume to be at what we call the equivalence point. Okay, so that's my picture. But in A, it says before you titrate. What does that mean? Before you add any of that stuff in. Kyle, what do you have? Just weak base, all by himself. When weak base is sitting there all by himself in water, he dissociates in the water. And what two things, Matthew, does he produce when he dissociates? Thank you. His conjugate acid and hydroxide. And if you have 0.3 molar and he's sitting in water, we allow him to dissociate minus X plus X plus X. We don't have to do this anymore because we've done it, I think, enough. At least I thought we had. Maybe not. Maybe we still need to do this to help us see what we have with dissociation. But since this is a base, and I know he's a base because he makes hydroxide, Kb is going to be equal to X squared over 0.3 molar. Yes? It's always going to work that way. And on your test, you've got to be able to recognize if you have only a weak acid or only a weak base, then I just say K equals X squared over molarity. Yes? I mean, that's got to become second nature. That's got to become easy peasy, and I shouldn't have to do the ice chart. 1.8 times 10 to the minus 5 equals X squared over 0.3. X is going to theoretically be hydroxide. Yes. Yes, it's also going to be ammonium ion value. And so I'll be able to get the POH when I minus log X. I'll have to subtract from 14. So Hayden, did you get a value for that pH there? I think 11.365 sounds a little bit more like it. 11.365, but that's okay. All right. Now, halfway to the equivalence point, this becomes null and void. Once you start titrating, you don't have a weak sitting there all by himself. So dissociation becomes null and void. Get that up here. This is only important when the substance is all by itself and nothing else is present. Is that important to know? Yes. So let's take our handy dandy eraser and let's erase this part. Let's erase that part. Let's erase all of this except for the ammonia because I still have the ammonia, but now I'm going to be adding H plus to my ammonia. When I titrate, H plus gets added to my ammonia. What do I make? Ammonium ion. I make only conjugate acid. You know what that also could look like? It also look like this. NH3 plus H3O plus yields NH4 plus and some water. That's the Bronsted-Lowry way. This is more of what we call the Arrhenius way. Both ways are valid, but you got to know that way too. You can write H plus as H3O plus, yes? So if you do, then that means H3O plus is on one side and water's on the other side. Okay, now how many moles of NH3 do I have? Because when I see one of these single arrow guys, I got to do some stoichiometry, which means I got to have moles. Got to have moles. So what is 0.3 times 0.05? 0.0150 moles. Okay, so that's what I'm starting with. So question, Kelsey, what value of H plus do I have to put in to be at the equivalence point? Let's do that first. Okay, to be at the equivalence point, 0.015 moles gets added in. So Janae, if I want to go halfway to the equivalence point, how much H plus would I add in? Half of that. What is half of that? It is 0.0075 moles. So I'd have to add in half the amount that would allow me to be at the equivalence point. This is half, agreed? So this is called halfway to the equivalence point. Now, Austin, who's my limiting reactant? The H plus. So I subtract 0.0075, subtract 0.0075, and add 0.0075. And Stephanie, what do I discover when I get here and I go stop, look, and listen? What do I have? What do I discover I have when I stop, look, and listen like I'm supposed to? I do. I have a buffer. And it's a special buffer, Ira, called a who? A perfect buffer. What is true when you have a perfect buffer? Because anytime you have a buffer, you think HH. What is true, Mariah, when you have a perfect buffer? What is true? What's the HH tell me when I have a perfect buffer? Thank you. Because if I have a buffer, this needs to come to mind, HH, and Ka times moles of weak acid over moles of conjugate base equals H plus. And if I have a perfect buffer, it means this value is 1. Because 0.0075 divided by 0.0075 is a ratio of 1. That's what it means to have a perfect buffer. It means that value is 1. Thus, Ka equals H plus. What else does that mean, Kyle? If the Ka equals EH plus, what can I say about pH? What about the Ka? Minus log of the Ka equals pH. All right, so I had a message on Edmodo last night from somebody, and it said, I don't understand why the owl is saying that minus log of Ka is the pH. And I immediately said to myself, they're saying that it's a perfect buffer. Because if the Ka and the H plus are the same, then the pKa and the pH are the same. Yes? So the minus log of Ka is the same thing as the minus log of H plus if it's a perfect buffer. You need to know that. Yes. Yes. So that comes with practice. That comes with studying those notes. And so this is what we have. Now, here's the problem. You weren't given the Ka. But, Matt, you were given the Kb. Can I get the Ka? Sure, because we know that Ka times Kb is always Kw, 1 times 10 to the minus 14, 1.8 times 10 to the minus 5. Can I figure out Ka? Sure, I can figure out Ka. 5.6 times 10 to the minus 10. 5.6 times 10 to the minus 10 for my Ka. So if I will minus log 5.6 times 10 to the minus 10, that will give me my pH value. Okay? Who's got a pH value for me for perfect buffer? It's going to be basic, I know that. Is it 9 point something? $9.25. I thought somebody said 2.5. I'm like, woo! 9.25. 5. Okay. Why is the pH going down from where it started? Because you're adding H+, strong acid. What happens to the pH if I add strong acid? It goes down. It gets more acidic. Still a buffer, but it's gotten more acidic. Yes? Okay. What about if I now have equivalence point? So I come up here and I say, all right, this is going to change a little bit. Now I'm at the equivalence point for adding in H plus to an H3. Let's see what happens. 0.0150. Now, who is limiting, Matthew? Neither of them are limiting. They are both, if you will, limiting, or neither are limiting because they're the same. It's a complete reaction. We are at what's called the equivalence point. The goal of the titration is to get to the spot where there's only conjugate left or only product left and nothing on the reaction side, reactant side for the reaction. Does everybody see what that's called? Equivalent point? Equivalent point? Equivalence point. They're equivalent. They're equivalent. So there's nothing left on the reactant side. There's only product. So, Hayden, stop, look, and listen. What do you have? Stop, look, and listen. What do you have now? NH4 plus. All by himself. What's he do? NH4 plus. What does he do? He dissociates with the water because he's acidic. How do I figure out X or pH? Ka equals X squared over molarity of the NH4 plus, which is from the rice chart. Yes. Yes. So you mean A was rice and C was rice? Yep. It was. And B was perfect buffer. Ka equals H plus. You need to get good. You need to get good at looking at those different spots. Not that we go from A to Z with titrations, but we have to know about the different spots. We have to be able to do the titration reaction. We have to be able to do that. Okay, now here's an issue. I don't know what total volume is, do you? And do I need it? I most certainly do, because I need molarity of my weak acid, my conjugate acid. I need molarity, and I don't quite have it. So let's go back to the picture I tried to draw for you, which is very important for a good AP Chem student to recognize what volume needs to be added. What did we say is going to be true? If this molarity is 0.3 and that one's 0.150 and you want to be equivalent, what are you going to have to do to this volume to know volume that needs to be added up here? You're going to need to double it. The volume that needs to be added is 2 times 0.05 liters. Do you see why? Do you see why? If their molarities are 2 to 1, then their volumes have to be 1 to 2 to give me equivalent moles. To give me equivalent moles. To give me equivalent moles. Okay, another way of looking at it is volume added is moles added divided by his molarity. Okay? Another way of looking at it. Or you can eyeball it like you should be able to over here. So that means that the concentration of my NH4 plus is 0.0150 moles over 0.1 plus 0.05. 0.150 liters. Agreed? Is that total volume? Okay. So that gives me a molarity of 0.1 molar. And then I just simply say Ka equals x squared over 0.1 molar. And Ka was 5.6 times 10 to the minus 10. So when that gets multiplied by 0.1 molar, it's set equal to x squared. And I'm able to square root both sides. Okay? If we're awake, if we're with me, now, if we're awake, do we see that? Do we see what I did? I have the molarity of the NH4 plus. So I'm now back at dissociation. I do Ka equals x squared over molarity. Okay? It's a matter of wrapping your mind around all the different pieces that we have. All right, so this is what I'd like for you to do. pH is going to be somewhere down in the 4-ish, 5-ish range, okay, because of the equivalence point. If there's nothing left but weak acid, it's going to be an acidic pH. I want you to take the quiz. You picked up 2 quizzes today. They say class set on them. I want you to take the quiz. It says quiz number 2, I believe it is. Yep. Quiz number 2. And you're going to try this front and back right now here on paper. And you may collaborate on this quiz. It's an NIMSY quiz. So it's not going to be just like this titration. It's going to have components of the titration in it. So if this preps you a little bit for this one. Now this one's going to be different though, because if you have a titration here at all, it will be a weak acid titrated with a strong base, like your question number 1 that we did the other day before this one. But the concepts are still all the same, whether it's base titrated with acid or acid titrated with base. So everybody take out your quiz, pick up today. Quiz 2. Quiz 2. I'll pull it up for us, but I'll let you work on it for about 10 or so minutes, maybe 12 minutes max. 12 minutes max, yes, you may.